I'll run you through a cartoon that explains this, which is not based on any Bayesian principles. So it doesn't demand that you adopt some kind of Bayesian mindset to see this. So we're talking about a school project it was an empirical project about whether gargoyles prefer pigeon or chicken for dinner. So the null hypothesis says they're indifferent. The alternative hypothesis that says they have a preference. So the person in question tested 62 gargoyles and found P equals 0.05. How diagnostic is the result? So first, it's important to note that if under the null hypothesis, every p-value is equally likely to occur. Also deeply counterintuitive to most people, right? So if the null hypothesis is true, you're just as likely to find 0.5 as 0.05 as 0.005. So that's just the way they are defined. So under the alternative hypothesis, so when there is an effect, small p-values are more likely to occur than high p-values. But the exact shape of that distribution depends on the size of the effect. So if you have a large effect, then small p-values are much more likely than large p-values. And if the effect is modest, that's less pronounced. So you can have all sorts of different distributions for your p-values depending on the strength of the effect. We can discuss the diagnosticity of a p-value as the degree to which it's more likely to occur under the alternative hypothesis than under the null hypothesis. So in this case, you see the distribution of p-values under the null, you see it under the alternative, an alternative, I should say, and the diagnosticity of that p-value of 0.05 is simply the height of the ratio of the height of the curves. So that p-value of 0.05 is only 1.5 times more likely under the alternative than under the null, and that's simply not very impressive. Okay, so far so good. But obviously there's a problem with this analysis. So every true effect implies a different shape and a different diagnosticity. So how can we possibly select the right shape? Well, we can't select the right shape because we don't have a crystal ball. But what we can do is we can cherry pick the shape that gives us the highest possible diagnosticity. So out of all the possible curves we can get, we pick the one that gives us the largest distance between the largest ratio between the heights of the curves, the green curve and the blue curve. So in this case, the one that was cherry picked gives us a maximum diagnosticity of 2.5, right? So in this case, the p-value is 0.05, and you may think, oh, 1 in 20, this is good evidence. But actually, the relevant number is 2.5. The data are only, the p-value is only 2.5 times more likely under the alternative than under the null, right? That's not very surprising. So this is known as the maximum p ratio, MPR, and it was discussed by several people, Vovk and Selke, Bayari, and Berger. So it's provided automatically in the JASP statistical program that we have developed at the University of Amsterdam. And I won't talk a lot about JASP today, but it is in there. So you see, this is actually an example. You tick the box, Vovk-Selke, maximum P ratio, and that is then what you'll get over here in a table. So what does this mean? So this means that when you have p-value of 0.05, it actually doesn't mean much in terms of evidence, in terms of diagnosticity. So that's a really big problem. So people have argued for more strict cutoffs, stricter than 0.05. And yeah, based on this line of argumentation, I completely agree with that. So it would be, well, very rash and imprudent to reject a null hypothesis based on a p-value near 0.05. Okay. So, well, that's actually what this slide says as well.